Hello, everyone. Welcome to my State of the Typelevel address, or what's new with psychorhomorphic prepomorphisms. No, actually not. So today I'm going to talk a bit about what Typelevel is, what's in Typelevel, and I hope I picked some of the stuff in there which is not already well known, because like Scala Z is already mainstream and Shapeless is like it's old already, so everybody knows how to use that. So I just picked some gems from Typelevel, hopefully, and but just for a quick show of hands, who of you is using one or more Typelevel libraries in production? That's quite good, actually, given that Typelevel didn't exist until 2 years ago, so it was founded in early 2013. Obviously, the libraries which are part of Typelevel are sometimes older, but the initial conspiration was carried out by Miles, who's here, and Eric Ostheim and Tom Switzer of Spire, and me at the NE Scala Symposium 2013, and the domain is actually older, so the typelevel.org, I think, if I remember correctly, I bought it when I heard about TypeSafe, so I thought what would be a cool name to have, so I bought typelevel.org, not knowing that it would at one point consist of so many great libraries. And since then, since this initial conspiration, we've added a couple of new libraries there, and we've got a SPT plugin now, and we also have got a Scala fork. So most of you probably heard about that, and there's going to be a panel discussion about that later today. So yeah, but what's the goal of Typelevel after all? So we want to provide a good set of Scala libraries, which should still remain fairly independent, and we have maintained that. So the original libraries, Scala Z, Shapeless, and Spire, are still completely independent of each other. And all of those should have in common that they value type-based design and reasoning. So many concepts are actually borrowed from Haskell. And the idea is that we want some general supplements for the Scala standard library, stuff which is lacking in the library or where there are known deficiencies. And we kind of want to embrace Scala and the unique features of the language. So, for example, the type class support, but also path-determined types, or several other features, macros, for example, in order to provide some good idiomatic Scala code. Not all projects in Typelevel actually satisfy the same design constraints. So, for example, Spire is very happy to use some quick and dirty hacks to get performance. Although, yeah, so Eric and Tom, they're pretty serious about performance. They still write very good code, and they have very different. So they're happy to have some illegal monoid instances in their project, for example, which we kicked out of Scala Z because they're unlawful, and we don't want police problems. And this is a good thing because, like most developers, also in our developer set, we have varying opinions about what should constitute good code. But in the end, what is common amongst us that we want to leverage the compiler, so that the compiler does more for us. Yes, as I already said, many projects are heavily inspired by Haskell, which you can, for example, see from Scala Z, which started out as basically a port of the most important Haskell type classes to Scala. So what's in there? As I already said, these are the initial libraries which we started, and then we've got some more. So we've also got testing in there. So Specs2 and Scala Check are also in our under umbrella, and Scodec and Scala Stream. I'm going to talk about Scodec today. Who has heard of Scodec? Okay. Scala Z Stream is a library by Paul Chusano and Runar Bjarnason, which does stream processing and is kind of compete with Akka in certain aspects. And at this point, you might wonder if the condition for inclusion in Typelevel is the project starts with S. But we actually have more projects. So this year we finally had to give in and allow non-S projects in there. So we have Organaut, which is for JSON processing, Discipline for law checking, as the name already says, and Monocle, which is a lens library, and I'm also going to talk about that today. And yeah, some more libraries, most of them, so these are the largest ones. There are a couple of others, some helper libraries, and as I said, the SPT plugin, but I'm going to mention them briefly at the end again. So what's the plan for today? We are planning to go on a whirlwind tour through Typelevel and just as the different London neighborhoods are different, also the libraries in Typelevel are different, but I hope I can establish some common theme today. And first, let's start with performance and numeric programming. So working with numbers, I'm sure all of you love numbers, especially floating point numbers. And the kind of the historic problem in the JVM land is that we always use fixed precision arithmetics as the default. So presumably, most of you use just float, double, int, or long by default in your programs. And in most of the time, that's OK. But actually, I mean, we're running on a virtual machine anyway. So we're abstracting from the underlying hardware. So there's little reason that we should actually be forced to use 32-bit arithmetics from the start, because we usually want correct programs first. And then we can start on optimizing. So we can use big int and big decimal from the standard library, from Java or the Scala wrappers. But what if performance is a concern? So Eric Osheim likes to say you can use big int if you hate performance. So he's got some ideas about that naturally. So Spire actually started out as a pre-SIP. So I think the original goal was to actually bring it into the standard library, but then it evolved from that. It was initially presented at Scala Days 2012. And it was a draft about the new numeric stack for Scala, basically, because I mean, Scala has a couple of numeric traits and also some data types, but Spire basically does it from the ground up. We have in there types, type class, and algorithms, so it's quite a lot. For example, we have the full numeric stack like monoid, rings, and there are even more lattices and different algebras. It is quite a lot there. And then we have data types. So we have a type for natural numbers, we have a type for rational numbers, and so forth. And what's new here is we also have they also have univariate polynomials, algebraic numbers, and computable reals. And I'm going to talk a little bit about these creatures in a moment, and also random numbers. So basically, whenever you need something which kind of looks numeric or algebraic, it might be good advice to have a look at Spire, and it's also widely used in production, so it's quite stable these days. So why should we not use floats? This is the reason, because floats just behave in a completely unpredictable way. I mean, they are predictable if you're familiar with the standard, the IEEE 754, which has been kind of designed for scientists and analysts who know how to use how to compute error bounds and stuff like that. And with our day-to-day programming, we don't necessarily want to care about that. We just want numerics which in some way are precise or are correct. We don't want to deal with error bounds checking and stuff like that. And I mean, if you use them like that, this makes perfectly sense from a hardware point of view, because there's only so much precision you can cram into 64-bit. But this is really not something we want our software to produce. So if you have 2 times 1 0.15 and 0.1 plus 0.2, we really want that to be the same. So this cat is not amused about this kind of semantics. So we really want to do something better. So as I said, one of the examples here are computable reals. So the assumption, we are going to make a couple of assumptions here, because no 2 numeric algorithms are the same, and you always have to be very careful about your assumptions you make about your inputs and also the kind of output you want. So first assumption is performance is not a concern. So you want precision and you want correctness, which is usually the kind of thing you should do in the from the beginning. So you should care about correctness first, and then maybe later on care about performance. And also the last assumption, which might be a little bit confusing, is that we're not interested in intermediate values, but it's also sometimes the case. So if you're doing some long-running computation, you don't necessarily want to look at the intermediate results, just at the end result. And what do we do as functional programmers if we are dealing with any sort of data transformation? We treat them as functions, and we can actually do the same thing with numbers. So now you might ask, how is a number a function exactly? But there's actually a very nice branch of mathematics talking about computable reals. And I'm having a short math interlude here now. some of you have probably attended the lambda calculus talk, so I'm going to continue with this tradition of putting some formulas in there. So what is this about? So A is the number we're interested in. So this is the actual real number which we want. But there are uncountably many real numbers, so we can't all represent them some way in our memory. So we need to do some approximation. And what we can do is we can have a function which approximates this number with some precision metric. So we say we can plug in 100 here, and then we have a function which says that if you compute that on 100 and the predecessor is less than A and the successor of the function is greater than A, and then we can, if we want to have more precision, we can just increase the n and we get more precision and even more. And so during the computation, we don't necessarily have to decide on the precision. We can just defer the decision to some point later. And the good thing about that is that you can basically increase n as high as you want, and your approximation gets better and better. Obviously, it takes more memory to represent your number, but you don't have, like in float or double, you don't have to specify right from the start that you want 32 bits of precision. You can have 1,000 bits of precision if you want. So how is this actually implemented? Spire has a class called serial, and it's C-real, not serial. And it offers a function called toRational, and it takes this precision parameter and gives you a rational number, where the denominator of this rational number is 2 to the power of p. So you always get p bits of precision. And all these arithmetic operations internally work with slightly higher precision. So why is that? Imagine if you want to add two numbers with 32-bit precision. And the result, you want to have 32-bit precision. You might get rounding errors. So better compute the internal, so better compute the summands up to 33-bit precision, and then figure out the rounding errors, and then round it back to, truncate it to 32-bit. And so you have the case that automatically the precision inside your computation increases in a way that you will still get the best possible approximation if you're asking for the result at the end. And that's why I was saying that you don't want to look at intermediate values, because you only ever get the best approximation when you're done with your computation. And the good thing about that is really intelligent about that. So you never do too much work. It's always just the amount of work needed in order to give you the approximation you wanted to. And while this might sound terribly academic or some way, so that you can't do anything useful with that, you can actually represent a lot of common numbers with that. So for example, you can represent pi, basically any real number which you can produce by an algorithm. And pi is kind of the best example for that, because there are good algorithms which you can say, I want p digits of pi, and it will just compute it up to that point. And you can compose these numbers in many ways. So you have all the standard operations. This is from the Scala doc of this real type. So you have plus, minus, all the different things. You can compute the power, and yeah. So it goes on for a while after that. So this is really a good example of how functional programming to the extreme. So you treat your numbers as functions can help you write correct code, because you abstract from your precision during your computation, and in the end you plug it in, and with just plain old function composition, you get magically the right result. The advantage here is that you can be as precise as you want, and the decision about the precision can be deferred to the end. So you might even ask the user for that. And also it supports a wide variety of operations, so you can implement basically whatever can be computed in a finite time. The disadvantage is not all real numbers can be represented. As I already said, there are uncountably many of them, and you only have idealized countably much memory. And also, you don't really have reliable equality, because what if you want to check if something is 0? Like, you have to check whether all digits are 0, so you have to basically ask for an infinite precision, and that's impossible. You can sort of alleviate that by saying, I want it to terminate for everything non-zero, and I'm willing to have it not terminate on exactly 0. So there are certain ways around that, but it's not really reliable. And also performance reasoning is difficult, because the JVM hates function composition. And if you're building a huge chunk of function composition, then you might be lucky that the hotspot is able to kick in, but sometimes you're not. And it's kind of difficult to see if you're just getting a value of type real, how long will it take to be evaluated? But as I already said, it's an assumption that performance is not a concern, and in most cases, if you actually want to print something to the user, you still need only 32 digits or something like that. But it's good to know that internally it uses the best approximation possible. All right, let's move on to a different topic. We're still talking about immutable data here, but I'm going to make a switch. I'm sure you all know what that is. So this is a plain Java bean, and this is the standard way. This is a standard way of representing data in Java. So you have getters and setters, and if you have a nested object and want to update something deep down your hierarchy, what you do is you do this. You have a cascade of getters, and then in the end you set the name of something, and that's the state of the art in Java. And what do we do in Scala? So in Scala we use our beloved case classes, which have been also mentioned earlier today. So we like to put all our data in case classes. And what do we want to do if we want to update the name of the person which is the head of the department in the company? So what would you do in Scala? So you would have to write this. So you have all these copy functions which the compiler helpfully generates for you. But this is kind of, you can kind of still understand this code because there are only 3 layers of nesting. But imagine you have 5 layers of nesting or 6 layers of nesting. Yeah, you don't really want to do that. So luckily, we have again a concept from mathematics. And this is the co-state, co-monad, co-algebra. And this is the equivalent to the Java member variable update technology. So we can once again jump to mathematics and look what they have. And if you are now expecting a definition of that thing, I'll have to disappoint you because it's not going to happen. Instead, I'm going to talk a little bit about Monocle, the lens library for Scala, and it even has a fancy logo. It's actually the only type-level project which has a fancy logo. So if some of you are like very skilled in graphic design or something like that, we could use some logos. Typelevel has a logo, but not the libraries in there. Actually, this library has been inspired by last year's talk at Scala eXchange by Simon Peyton-Jones. And the story goes as follows: that Julien Truffaut, who is the author of that, wanted to try something out with lenses. And Scala Z has lenses, and Shapeless has lenses, and he didn't have very good internet connection, so the download from Maven Central failed. So he thought, like, okay, I'm doing my own. Now this happened. So this is a true story. Julian told me that. Yeah. So case classes revisited with Monocle. Those are basically the same case classes, but with some additional annotations. And as you can see from the import statement, those are actually macros. Those are annotation macros, so that requires macro paradise. But if you just slap those annotations on there, you can use a much better syntax. As you can see, there are no copy methods involved anymore. And what's going on? So you have this company is still this value, with this, it's still a value, and then you apply a length, and then you have some sort of selectors here. And this looks really odd because if you look back here, you have a case class, and you have IT and HR are not those are methods on the object, on instance of company. They are not methods on the companion object. But you can see here they have been lifted to the companion object by this macro. And now you can compose, these are some sort of first-class setters and getters, and you can compose them together and set a new value. And the underlying idea is that these are basically functions which describe a way to look into a data structure. So you have a whole bunch of data, and then you have a focus in there. So, for example, here this would be the company, and you have to put a focus on the IT department here, and then you can compose these things together. So if you have a big thing and a smaller focus in there, and then you take this smaller thing and put an even smaller focus in there, you can compose this together. And the good thing is here that you don't have to write that all the time. You can just pull that out. So you can take this stuff, put it in parentheses, move it into a value. So you put it to a variable, and then you can just write this variable here. So it's just a regular function composition, basically. And this is the coolest thing ever, because now you don't need to write all those copy things, and you don't need to be ashamed of being so boilerplatey. I can only recommend trying it out. So there's obviously a lot more to say about Monocle, and there's a very rich theory behind it. If you want, you can Google for Edward Kmetz's lens library or for this repository Monocle. There are a lot of good examples in there. I unfortunately couldn't bring all of them. So it's nearing its 1.0 release. There's actually already a milestone out. And it comes with batteries included, so it already has a lot of lenses predefined for working with the standard library. And there are also ways to, for example, focus on all elements in the sequence. So let's say you have a list of companies, and in all those companies, you want to increase the salary of some person, of the manager or whatever, you can just take a lens, or it's not actually a lens, it's a traversal, which is kind of a lens, but not quite. And it allows you to focus on each of the on any of the companies in this list and update all the data in there. And that's really nice because this is functional programming taken to the extreme, because you're composing, it's just again composing some functions with additional structure. And yeah, so lenses can be auto-derived, but if you hate macros, you can also write them by hand. It's a little bit boilerplatey, but in the end, for every field, it's like 1 or 2 lines of code, and you can just slap that into the companion object and be done with it. It's essentially the same what the macro does. And it's likely to supersede Scala Z lenses, so we have in Scala Z have a lens implementation as well, but we're probably going to deprecate it with the new release because Monocle does everything we do, and it does it better. There are still shapeless lenses out there, but they have a different design approach. And if you want to know about that, you can pester Miles. He's around. But this is another good point. In Typelevel, we try to avoid redundancies. But if there are really 2 competing designs, we can still allow for that because, as I said, not every project is created equal. So you might have different things you're valuing. OK, up to the next thing. This is a quick survey about libraries to deal with JSON. And actually, while compiling that list, I found out that Raptor.json is by John Pretty. He's also around. So Raptor.json is able to talk to John, and John is able to talk to Argonaut. But Raptor.json is also able to talk to Argonaut. And I talked with John today about this, and he was wondering, could we actually make a cycle out of that? And that kind of scared me, but he actually considered it. So we have quite a lot of JSON libraries, and we don't actually want. I'm not actually going to talk about that because JSON is like, it's everywhere, and I promised you to pick some nuggets which you probably don't know. And that's why I picked a library for dealing with binary formats. So if you're deep down in the trenches implementing an RFC whatever for TCP or stuff like that, if you're into that sort of thing, we also have a solution for that. And it's kind of difficult to find a good library in the JVM land for that, because everyone is obsessed with human readable formats like XML, JSON, and stuff like, or JSONX or whatever, XMLJ, whatever there is. And there is no really good story about binary formats in an idiomatic functional style. So Scodec solves this problem from the ground up. It has a fast byte string implementation. It is actually able to compete with the Yaka byte string implementation in some benchmarks. It doesn't compete in other benchmarks, but still. And it has some really nifty features like hex and binary string interpolators, which are based on macros. So if you make a mistake, the compiler will actually yell at you. And it has support for variants or sums or whatever you want to call them. And this is actually a thing which Scodec gets right, because usually if you have some serialization library, it's concerned with sequences of data. But if you have choices of data, the story is usually worse. So it's kind of, I like to make this analogy with meta and anti-meta. So meta won, and nobody's really observing anti-meta. And the same in programming. So sequences are everywhere, but choices are rare. So nobody really deals with choices. And it supports generic programming via shapeless. And what does that look like? So, for example, if you have a data format which could consist of 3 cases, so you could have an integer of 32-bit, you could have 8 consecutive booleans, or you could have some ASCII string which has a length in front of it. So you say how many bytes are going to follow, and now you want to kind of decide. Now you want to kind of determine how to know which of these branches you're actually looking at, and the story here is this is a kind of intermediate parser, and it is still requiring some information about how to disimmigrate. And this is what happens with discriminated by. So you can say, I'm going to look at a byte before. So I'm going to look at one ASCII byte before my actual data. And if it's an I, I'm going to choose this one. If it's a B, I'm going to choose that one. And if it's an S, I'm going to choose the last one. And now you might ask, how do you actually know that you have exactly as many cases in the union as you specify here? Well, that's some deep shapeless magic. So this size data type, so this size looks completely innocent. But what it does internally is it looks at this number of arguments you've passed, represents it as a type level natural number, and it will match this up. So it will complain if you have 4 cases here and just 3 cases there, or the other way around. And this is really nice because now the compiler gives you full help for these kinds of situations. And there's a lot more in ins codec, and this is actually lifted from an example Michael Pilquist showed me. It's also in the Scala doc, I believe. But there are a lot of other ways to construct these kind of codecs because all those specifications are usually written in a very different style, so you have to have different styles for different kind of data. And you can also use it like the Scala parser combinator, so it also has this tilde operator, which you know from Scala parsing and stuff like that. So it offers quite a lot of features how to construct these binary codecs. So how does it actually, how do you actually get all that magic to work? This is based on Shapeless. And Shapeless recently got some additions on this generic programming. And basically, Shapeless also started out as a conference talk. This was kind of a proof of concept whether Miles could scrap your boilerplate from Haskell work, and then it kind of escalated quickly. And now we have all that stuff. So type classes, as you know, abstract operations over data. So you specify an abstract set of operations, and then you can have data arbitrarily implementing it, and it's modular, nicely modular, and stuff like that. And many type class instances, though, are completely generic. So if you're writing a codec for some standard data or some JSON serialization or XML serialization, it's usually completely mechanic. So it's completely obvious how to write. And though the question is, we are abstracting all the time. So we're taking type classes to abstract operations over data. Can we also abstract our type classes? Yes, we can actually go deeper. And there was, at one point in Shapeless, there was a type class called type class. It has now been removed, but it will be reintroduced again. And it's actually a type class abstracting over type classes. And it's a kind of a way of capturing the essence of what type classes mean. So can you actually how you can actually compose type classes into larger instances. And I have a kind of a motivating example here. So this is the list data type you all know and love. And if I told you, please write me an ordering for that list. So I assume you have a comparator for that T, write a comparator for the whole list. And this is completely trivial because, you do just lexicographic ordering. So you check, nil is always less or equal than is lesser than cons. And if you have 2 cons, you have to compare the head, and then you have to compare the tail. So it's completely mechanic. It's trivial to write, and it's much copy and paste, or as Paul Phillips would say, copy make pastington. And if you copy and paste, you introduce errors really quickly. So assume we have a point data type for 3 dimensions, and you have p1.x, p2.x, p1.y, p2.y, and so on, and you introduce errors pretty quickly. So you really want the compiler to help you there. And Scala C already does toString and equals because it's trivial to write. And Shapeless can do even more with that. So you can basically describe for an arbitrary type class how to compose instances into larger instances, and it will do that for you. And I actually have a small demo here. This is working in a development branch of Shapeless, which will probably end up in the next release. And this is an example I picked for diffing values, which is a credit to Stacy Curl, I believe. Yeah. And it's a way of looking at data and kind of finding out the difference between 2 values of the same type. So for integers, for example, it's really trivial. So if you want the difference between 2 and 3, oops, delta, exactly. So you have the difference here, and it's 1, obviously. And if you want to compare 2 strings, you can also do that. And those instances are hard-coded because integer and strings are kind of primitive data types. But what if you are looking at, what if you want to look at case classes and you want to implement such a diff for case classes? It's completely obvious how to do that. I mean, you just have a look at all the different all the different values in your case class and compare them one by one. And just to prove that I didn't prepare anything here, I'm just going to define a case class from scratch. So let's say we have a case class foo, and we give it an integer value, and let's say another integer value. And let's say a string. So we have now defined a completely fresh type class. Let's define two values of that. 0, 0, foo1, foo2, say 2, 0, 2. And now we can say foo1 delta foo2. And the underlying macro somehow looks at the case class and will, what did I say wrong? Oh yeah, the underlying magic looks at the case class and will analyze what's going on there, what values are in there, and you will see. So the first item has a difference of 2, the second item has a difference of 0, and the last item has like foo1 and foo2. So you see the difference here. So this is just an example for like you can have a look at the code in there. It's really not that difficult to write. And I can only encourage you to get rid of your boilerplate in your type class definitions and instance definitions. There's actually a more general abstraction which is hiding in there. So you can actually have lazy implicits because you have the problem if you want if you want to do that. So you have like if you want to compute the delta between two lists, you are looking for a delta instance for list of t. And you need the delta instance for t, and then you need the delta instance for list of t again. So you have kind of a recursive implicit lookup. And it turns out that you can actually write it in a way that is completely natural. So you just have to wrap it in a type constructor called lazy in shapeless. And it's coming up in the next shapeless version. And just explaining how it works is completely out of scope here. But it allows you the implicits to write implicit in a completely natural way. And if you look at them without knowing what's going on, you would say, oh, this is going to diverge, right? So this is not going, the Scala compiler is not going to able to infer that, but it actually works. And it's kind of looks at the recursive invocations and tries to figure out what's going on. And this is also very awesome. It's 20% cooler than the original design of type class. So you should all maybe try it out and find out if it's suited for your use case, but it probably is. Okay, so maybe the next thing on my agenda, you might have been waiting for that one. Typelevel Scala. So it's our fork which has been announced earlier this year. And I'm just going to give a quick overview here because there's going to be this panel discussion later today. And what is it about? So we obviously have different interests we all have different interests in the Scala compiler. And as you all know, the Scala compiler is kind of focused on stability right now, which is a good thing because it helps adoption greatly. But we also want to have some playground for experimental new features. And that's basically what type-level Scala is about. We have less strict stability requirements, and we can kind of try out new experimental features which we've always wanted to lay our hands on. And the underlying idea is that features which have been added in type-level Scala can eventually move back to type-safe and the other way around. So we really want to stay compatible with the original compiler. And if you introduce any incompatibilities, we would hide them behind a flag, so that you could enable our fancy new whatever with a flag. But if you still want to compile your old code, you can still do that. The reasons are that we have different, as a community, we might sometimes have different interests than type-safe, which is obvious because naturally open source communities have very different interests than commercial communities. And also the type-level project could benefit from new compiler features. So we even have a code base where you can try that out. And TypeSafe is helping. TypeSafe is already doing some kind of thing like that. So they have this community build, which builds a lot of source code against upcoming Scala versions, and potentially we could also enable that for our fork, so that we can still try out whether everything still works or something breaks. Yeah, we want to see a language which is actually open and moving quickly. So that we can, as I said, that we can try out some changes with, if they were introduced in the official compiler, might turn out to be a bad design, but they cannot be taken back, because if something is the official compiler, people start depending on it. You can't just roll that back. I mean, that's how the world works. And in an open source alternative compiler, we could try out potentially more things and break more often. Also, another point is that we can have a greater diversity. So we can even try out some wacky stuff which nobody would even dare to think about in the original compiler. So there's a bit going on. This is a screenshot from the GitHub, which I did that, I think, 2 days ago or 3 days ago. So there's quite some issues open and also some pull requests. 12 pull requests actually already get merged, and some even got reviewed by TypeSafe, which is really nice. So if we can actually get feedback from the people who know their way around the compiler, because we all have no idea what we're doing. I mean, none of us has actually worked quite a lot with the compiler. It's just like trial and error. We poke somewhere and see what happens. It worked out quite well for these 12 pull requests already. Some are syntactic changes, some are also semantic changes, and there was going to be a talk by George about one of these major changes. It's called 42.type. I can just recommend going to his talk. Yeah, and it's entirely community-driven. So if you want to see some progress in our fork, just open an issue or pull request. That's basically how the community works. And if you don't have a pull request, you can just open an issue. That's okay, because even knowing what somebody wants from the compiler is already a good bit of information. Yeah, more of Typelevel. We also have some helper projects which we call contrib. So there's Scala contrib, shapeless contrib, and Spire contrib, and they contain some more experimental features, and they also serve to integrate between those main libraries. As I said, like Scala Z, shapeless, and Spire are completely independent from each other. But we have some conversions. So for example, we have a project which is able to convert between the different lens representation from shapeless and Scala Z. So if you're inclined to use both libraries, you can just include the contrib library as well, and you get some cheap conversions. We also have compiler plugins. One example is Kind Protector by Eric Osheim. So who of you knows what a type lambda is? Who of you likes writing type lambdas? I don't believe you. So it's a plugin which makes some syntax better in the surface code, and this plugin has already ended up in the Typelevel fork. So yeah, and the latest edition in our family project is Scala Z, Scala Test, or Scala Test, Scala Z. I don't know which direction. So it's one of these contrib projects by Brandon McAdams. So it allows you to use Scala Z data types in Scala Test matches. So you no longer have to worry about having no choice, because Typelevel has specs too. But if you want to use Scala Test, that's fine as well, because we also have bindings for that. Yeah, the last thing I'm going to mention is the binary compatibility. Martin has already talked about that today. We want to offer similar guarantees like Scala itself. So, for example, all releases in Scala set 7.0.x are binary compatible, but just backward compatible, not forward compatible. And we also already have a draft document which specifies these constraints. It's not published yet because it's surprisingly difficult to get it right. And some projects already satisfy these constraints. For example, Scodec or Scala Z satisfy them. And there's also an SPT plugin to help enforce this compatibility, but it's not quite there. So it has some bugs, and it's called SPT Typelevel. So if you want to use it, it also checks transitive dependencies. So if you're pulling in two different versions of Scala Z, it will actually tell you whether there's going to be a problem. But it actually needs some users. Okay, so what's next? We want to provide more integration between the projects, and obviously want to reduce the transitive dependency pain by kind of giving a vetted set of dependencies. And the next point is really optional, so we're not sure if that's something people want, but it's an idea to provide some sort of stable set of libraries which are guaranteed to work with others. So you could pull in some snapshot, and you will be sure that all the versions and all the libraries in there will guaranteed work together. Yeah, and also Scala.js ports, which is quite a hot topic right now. There's also 3 talks about Scala.js here, and obviously, last step, world domination. Questions?